Hi everybody and welcome to tutorial 3 of control systems. Today we're just going to go over how to get some transfer functions for a few different exercises. You can skip ahead to one of the exercises of your choice. Timestamps are there on the right. And with that, we will get started with number 1. Okay, so here we have the first exercise. It is a double pendulum system. The two pendulums are connected by a spring K. They both have massless rods with a length L, and there is an input force F of t. The first thing this question asks for is the equations of motion. In order to get those, we're going to need to draw the free body diagrams for both pendulums so that we're better able to account for all of the forces. So for the first pendulum, we have the force of gravity, mg. We have the input force, F of t. And what happens when we have that input force is it compresses the spring. The compressed spring wants to expand outwards, so it'll push out in both directions. So we have this opposing force here, K, and for now we'll write x1 minus x2, where x1 is just this displacement in here, and we'll write a proper expression for that a little later on, and x2 is that same displacement but just for the second pendulum. And then we also just want to make sure that it's very clear this is theta 1. And we'll do the same thing for the second pendulum. We again have the force of gravity, mg, and this is theta 2. Okay, so now the only input to our second pendulum is that spring force. And if you remember, it was being compressed, so it expands out, and we get a force in this direction, which is k x1 minus x2. And that kind of makes sense if you think about it. When we have an input force here, we do expect that at least a portion of that is translated all the way through to our second pendulum. Okay, so the next thing is let's get expressions for x1 and x2 in terms of theta 1 and theta 2. And in order to do that, what we can see is it's actually a pretty straightforward triangle. I'll draw it for theta 1, and we can just use the same one basically for theta 2. So our angle is theta 1. We're trying to get this displacement at the bottom, x1, and we know that it's applied at a distance of 1/2 L. So we have a hypotenuse of 1/2 L. So from there, it's just sine, right? So we get 1/2 L sine theta 1. And for theta 2 or x2, it's going to be kind of the same idea. We have x2 is equal to 1/2 L sine theta 2. Okay, so now I'm just going to plug these into our equations for the spring force, and then we will move on to the next step. Okay, so as you can see, we've replaced our x1 and x2 terms with the equations we came up with. So as you'll see, we'll be able to factor out a 1/2 L, and we'll do that in just a little bit. First, what we want to do is when we get our equations of motion, we're actually going to take the sum of moments about our center of rotation. In order to do that, we need the perpendicular component of every force, and we're going to do that now, so that we have just the component that's perpendicular to our arm here. So for t, our input force F of t, that's going to be just this component down here. And we know from similar triangles that this angle is going to be theta 1. And we have the same thing up here, where our angle is theta 1. And we also need to do it for our force of gravity. In this case, this angle is theta 1. Okay, and we do the same thing for all of the forces on our second pendulum, where here we have theta 2 and here theta 2. Okay, so the component of each of these that we want, so down here we want this bottom component, so we get f of t cosine theta 1. We want cosine up here as well, so it's just going to be this term times cosine theta 1. I'm not going to rewrite it all because we're going to simplify it a little further in just a moment. And for gravity, we want this component, which is going to be mg sine theta 1. Okay, and we do, again, the same thing down here. These terms are getting kind of messy and very big, and we actually don't need them to be that way. So we're going to apply small angle theorem to hopefully simplify the terms a lot so that we can write things a lot more neatly. If we have a relatively small angle, or if we can assume we have a relatively small angle, we can say that sine theta is approximately equal to theta, and that cosine of theta is approximately equal to 1. So again, this only applies for small angles, but we're going to use this here because we can assume the vibration is relatively small. Okay, so I have simplified and factored out L over 2, and we've applied small angle theorem, and we are now ready to write our equations of motion. So as I mentioned before, we're going to sum the moments about the center of rotation for each pendulum, so we will get 2 separate equations of motion, and we'll start with the first one. So what we want to do is we're going to consider the counterclockwise direction to be positive. So positive. And then we want to sum the moments. I'm just going to say around 1 or for pendulum 1. That has to be equal to the mass times the total length squared times theta 1 double dot. Okay? So that's really important that we set everything equal to that. Okay? So now we're going to actually add everything. And we have m L squared theta double dot is equal to, and our first force is positive, and we have to multiply by this distance. So we get f of t, right, because that was in the counterclockwise direction, or it would create a counterclockwise moment times L over 2. And this next one creates a clockwise moment, and that is k L over 2 theta 1 minus theta 2 times that same distance, which is L over 2. And our last term is the component of our gravitational force, mg theta 1, mg theta 1, which you can see also creates a counterclockwise moment, and we have to multiply by that by the total length. I want to rearrange this a little bit and put it more into a standard form. So we're going to move all of our outputs to the left side, and all of our inputs will keep on the right. And then we'll also make sure that there's no coefficient in front of our theta 1 double dot. And in order to do that, we'll divide everything by that. So to start, we get theta 1 double dot. And while I'm at it, I'm going to combine just these 2 terms here since they're both multiplied by theta 1. So I get plus, I'm going to open my bracket. So k L squared over 4 becomes k over 4m. That's times theta 1, but first I want to add. We get g over L theta 1. And then we also have to do this next term, so we get minus k over 4m theta 2. And finally, our input on the right-hand side, where we have 1 over 2lm f of t. Now it's time to just move on to the second pendulum. So we have the same idea here. We're again going to consider the counterclockwise direction as positive. You have to keep them consistent just on the same question. So we'll do for 2. And again, it has to be equal to m L squared, but this time it's theta 2 double dot. Okay? And we'll start with that. So we have m L squared theta 2 double dot equal to, and we have a force here that's going to create that counterclockwise moment, so that's positive, which is k L over 2 theta 1 minus theta 2 times this distance, which we know is L over 2. And then we have to subtract a gravitational component. Again, it's really similar to what we had last time, but in this case we get mg theta 2 times that entire distance is L. And just like last time, we want to rearrange this. We have our first equation up here and our second equation down here. The question asked for the transfer function between the output theta 1s and our input f of s. Okay, so we've rewritten our equations down here so that we didn't lose them, and we've cleared off a nice big space so that we can do the next part, which is we need to find the transfer function for theta 1s over f of s. Okay, so as you can see, that is in the frequency domain. Your transfer functions should always be in the frequency domain. So we'll do first equation. And we're going to assume all of the initial conditions are 0. If you're not given initial conditions, you can usually just assume that they're 0. It's best maybe to make a note of it. That's fine. You can just assume they're 0. And we're not going to leave it quite at that. We are just going to simplify. We get s squared plus k over 4m plus g over L, that's all times theta 1, minus k over 4m theta 2 is equal to 1 over 2 lm f of s. Okay, so now we're going to do the same thing for theta 2, and then hopefully we can combine both of them. So we get 2, and we have s squared theta 2 plus k over 4m theta 2 plus g over L theta 2 minus k over 4m theta 1 is equal to 0. Okay, and again, we're just going to group some of those like terms together. So we get s squared plus k over 4m plus g over L theta 2 minus k over 4m theta 1 is equal to 0. What we'll do next is we are going to rearrange this equation down here to isolate for theta 2, and then we'll plug that into our first equation. So I'm going to do that now. So we've cleaned it up a little bit, and I left just the two equations we need to combine. So we have here our term for theta 2, and we have up here our rearranged first equation. So we're just going to plug theta 2 into that. First, we're just going to copy down the part that doesn't change. It's g over L theta 1 minus k over 4m, and now we get k theta 1 over 4m s squared plus k over 4m plus g over L. And that is equal to 1 over 2 lm f of s. Everything is in terms of either f of s or theta 1, and it looks like we can just factor out theta 1 pretty simply and then move things over into the correct format, which is this. First, I'm going to factor out theta 1 from both of those, and we're almost done. Now we just need to divide both sides by f of s and divide both sides by this big term in the square brackets. So that is our transfer function. Just before we move on, there is a way to simplify this. What we can do is we can create some additional variables and we can plug them in instead. So what I'm going to say is that a is equal to k over 4m plus gl, and I'm going to say that b is equal to k over 4m. Now we can plug those in and hopefully we can rearrange it a little bit more easily than without them. This is just plugging in our new variables for what was there, and you can already see that it looks a lot simpler and it looks a lot more manageable now. So that's exactly what we're going to keep doing, is we're just going to try and simplify this denominator a little bit. All right, and there you have it. That is our final transfer function, and we are just going to leave it at that. Okay, so the last part of this question is to apply the final value theorem and get the final value if we have an input f of t equal to 2 newtons. So for that, we will need our transfer function. We can do this all in the frequency domain. In fact, we have to kind of. And that means we need to convert our input to the frequency domain. So if we have f of t equal to 2 newtons, that means we would have f of s equal to 2 over s. Okay, so the other thing is, now with our transfer function in that form, we can multiply both sides by f of s to get just our equation for theta in terms of our input. And we will do that right now. So we get theta 1 of s equal to 1 over 2 lm s squared plus a over s squared plus a squared minus b squared, all times f of s. Okay, so now that we have kind of that, we can use our final value theorem. We have the limit of s approaches 0 of s times theta 1 of s. Okay, so that should be pretty straightforward to apply. For that, we have the limit as s approaches 0, and we have s, and now our equation for theta 1, so we have 1 over 2 lm. And just remember that our a and b are both constants, right? So if we had the stiffness and the mass and the length, we could plug in numbers and we could have that completely evaluated. So we get s squared plus a over s squared plus a all squared minus b squared times, and I'm going to plug in f of s, which is 2 over s. As you might be able to spot, some things here are going to cancel out. And as s approaches 0, we will have this approach 0 and this approach 0. What we should get is 1 over lm times a over a squared minus b squared. Okay, so that's it for this question. Obviously, we could plug in a and b again, and if we had actual numbers, we could evaluate it at those, but this is just the analytical expression, and hopefully it gives you a good idea of how to approach these kinds of problems. Here we have our second exercise for today. There is a spring mass damper system. We are given some of the parameters. Both masses are equal to 1. We are given our damping coefficient over our spring constant. We're also given the zeta term. So the question asks us to sketch the S-plane pole 0 diagram. In order to do that, we will need the transfer function for this system, and to get started, that means we need the equations of motion. So first we're going to draw a free body diagram for each mass and then get the equations of motion from them, take the Laplace transform to get them into the S domain, and then we can rearrange and combine to get our transfer function. So first, mass 1, m1. We can see from the question that it has an input u of t, so that's an input force. When we have a force going that way, our springs will oppose that motion, so they will push in the opposite direction. So those are our two spring forces, and now we just need to know their value. The force from a spring is the spring constant multiplied by the spring's displacement. So here it's very simple, it's just going to be k x1, because our displacement is x1. And here we have to subtract the displacement of x2, right? Because when we compress the spring by x1, if x2 moves to the right a little bit, its positive direction, it would also obviously be compressed a little bit less than if we only had motion in x1. So we have k x1 minus x2. And from that, we can sum all of the forces acting on our mass. Right now we are neglecting gravity because we weren't told what plane this is in. So the sum force is equal to mass 1 times x1 double dot. Okay, so x1 double dot is going to be equal to our input force u of t minus our spring force will go k x1 minus this spring force, k x1 minus x2. All right, we're just going to continue on with that, and we'll do the second mass in a second. So we want to rearrange this before we take the Laplace transform. So we'll have x1 plus k x1 plus k x1 minus x2 is equal to u of t. So we've moved all of our outputs to our left side and all of our inputs on our right. We can take the Laplace transform now. I'm going to expand this at the same time, so we get m1 s squared, assume initial conditions are 0, x1 plus k 2k x1 minus k x2, u in the s domain. And one last step is we want to get rid of this coefficient in front of the x1, so we will have s squared x1 plus 2k over m1 x1 minus k m1 x2 is equal to u over s times 1 over m1. So make sure you do it everywhere when you do it, otherwise you might not get the correct, or you won't get the correct answer at the end. So we have to do it both to the left and right side when we're dividing everything by m1. Okay, we're going to factor out the x1 and the x2 just to isolate our variables a little bit better. So we get x1 s squared plus 2k over m1 plus x2 times negative k over m1. And that's still equal to 1 over m1 u of s. So that's it. I'm going to set that equation aside here, and we will do the second one. And now for m2, we want to do the same procedure. So we will have m2, its positive direction is the same way. And since we have the spring force pushing back on the motion here, the spring would be compressed a little because of that input force, which means it pushes out in both ways. That's why we had the direction that way on M1, but we'll have it the opposite direction on M2. And you can think of this kind of as a translation of that input force from M1 to M2, right? Because you would expect it to push both masses a little bit. So we get that. And we have k x1 minus x2. And on the other side, our damper opposes the velocity, so we get b x2 dot. All right, and now we just sum our forces. So we have the sum of forces on 2 will be equal to the mass of 2 times the acceleration of 2. And our input, we get k x1 minus x2 minus b x2 dot. And we rearrange because we want all of our outputs on the left and all of our inputs on the right. We get m2 x2 double dot minus, or plus, sorry, b x2 dot minus k x1 minus x2 equal to 0. Okay. I'm going to expand this and also take the Laplace in one step. So we get m2 s squared, again, assume initial conditions are 0, x2 plus b s x2 plus k x2 minus k x1 is equal to 0. Okay. And again, we don't want a coefficient here, so we're going to divide everything by that m2, and we get s squared x2 plus b over ms x2 plus k over m, I guess this would be m2, sorry, x2 minus k over m2 x1. All right, and now what we want to do is we want to group those variables, so we get x2 times s squared plus b over m2 s plus k over m2 minus x1, we'll write it as a plus, minus k m2. And that's all equal to 0. Okay, so now we're at the same point we were with our first equation. The only difference is this time what we want to do is we want to rearrange this for x2 so that we can plug it in, since we'll want the transfer function of x1 over the input u of s. So rearranging this for x2. We get x2 equal to, move that to the other side, and we will get k over m2 x1 all over top of this, so we get s squared plus b over m2 s plus k over m2. Okay, the next thing we'll want to do is plug this into this equation for x2, and then we can rearrange it so we get x1, our output, over our input u of s. So we have x1 s squared plus 2k m1 plus, here we plug in x2 and we get k m2 x1 s squared plus b over m2 s plus k over m2 times negative k over m2. And that is equal to our 1 over m1 u. Okay, and we factor out x1. So we'll do that. x1 times s squared plus 2k over m1 plus. So this is supposed to be m1, not m2. Then we have this part, so we get k over m2 times this in our numerator, and that makes this a negative sign, so we get k over m1 over s squared plus b over m2 s plus k over m2 is equal to 1 over m1 u of s. Okay, so a transfer function, I'm just going to write TF, is always going to be equal to your output over an input. So sometimes if you have multiple of these, you'll have multiple transfer functions that relate the various outputs to inputs or inputs to outputs. But in this case, we were asked for x1, and our input is u of s. These are both in terms of s. Okay? So I hope we can all see where we get that from at this point. It is going to be equal to, we'll have 1 over m1 in the numerator divided by this entire equation. So we have s squared plus 2k over m1. And at this point, I'm going to get these under a common denominator, and I'll move this to the numerator here. So we get s squared plus b over m2s plus k over m2. And here, that'll be multiplied. So we get the same thing. And then we will just have minus k squared m1 m2. So that is the analytical solution. The next step is we were given the actual inputs, so we want to plug those in to get a numerical equation for the transfer function, which allows us to find the poles and zeros, and then we can plot the graph that the question asked for. Both m's are equal to 1. I'm just going to write everything down here. So 1 over 1 is just going to be 1, and we'll leave that. S squared doesn't change. We have b over m2. So we don't have any exact values for those, but let's look at some of the things we have here. We get b over k is equal to 1. Well, we can rearrange that so that we get b is equal to 1k, or really b is equal to k. And the other thing we can do is we can rearrange this. So let's start, we'll rewrite it. We get b over 2 root km equal to 0.1. Okay, well, we can take the 2 out of the denominator and square both sides to remove that square root in the denominator, and with that we'll get b squared over km is equal to 0.04. We know that m is equal to 1, but we want to leave that in for now. So the other thing is we know that b and k are equal, or that b over k is equal to 1, so we can just cancel that. And we'll get b over m is equal to 0.04, And since b and k are equal, we can also say that k over m is equal to 0.04. And in this case, this could be m1 or m2. Doesn't matter, but it allows us to sub things in a little bit more easily. And as one final step, if we treat m as 1, which we know that it's equal to, we get k to 0.04 or b equal to 0.04. All right, so now let's sub everything in. So we get plus b over m is 0.04, s plus 0.04. So that one was pretty easy. In the denominator, we get s squared plus, so that's going to be 2 times k over m is 0.08 multiplied by s squared plus 0.04s plus 0.04. And then finally, over here, we get k squared. So it's going to be minus 0.0016. All right, and we'll want to expand the denominator as well, and this is going to be to the 4th power, or s to the 4th, which is very, very difficult to solve by hand or numerically, and it's best that you use MATLAB or a calculator to solve for that when we look for the roots. So we get s squared plus 0.04s, 0.04. In the denominator, we get s to the 4th. We have 0.04s cubed plus 0.12s squared plus 0.0032s and plus 0. That's going to be 0.0032 minus 0.0016, so we'll get 0016, the positive, right? Okay, we need to draw the system of the poles and zeros. The poles are the roots of your denominator, and the zeros are your roots of the numerator. So here we have question 3. It has 3 sort of separate systems that are going to be connected. We're going to find a gain between each of them so that we're able to compare the output of our mechanical system to the input to this initial electrical loop F of, or V of F. So to start, we need to write the equations for each loop or each system separately, and then we can combine them with those gain values. So to start with loop 1, EFS, and now we just need to remember from our electrical classes, we have a current IF going through RF, so this is going to be equal to the drop across our resistor plus across our inductor. So we get IF RF plus LF, and that's the derivative of the current. So we get dIF over dt, or what we can later describe as I dot. But what we're going to do is we're going to take the Laplace transform and rearrange this right away. The Laplace transform, oh, this is supposed to be t. So once we take the Laplace, this is of S, we get IF RF plus LF S IF. Rearrange, and we have IF equal to the F of S divided by RF plus LFS. All right, we got loop 2. So we start with our input, VG. This is currently of t because we haven't taken the Laplace transform yet. The drop across the first inductor is going to be LG dig over dt plus the drop across the resistor, which is RG IG, the drop across our next resistor, which is RFIG, plus our next inductor, which is LFDIG over dt. Remember that our g's are just a subscript, even though they're written kind of large. So we take the Laplace, and the last step is, again, we want to rearrange that, so we just have an equation of IG. Okay, and on to our mechanical system. In this, we have to make sure that we take into account the inertia of both these kind of separate circular systems, and then also it specifies a bearing friction, which we're going to treat as a damping. is a tau, and we'll call it tau m because it's going to be motor torque. So we'll start with that as our input, motor torque. And that is going to be equal to, we have a inertia here, so that is going to be J, and we'll call it M, times theta M double dot, so that's just the angular acceleration of this upper portion, and then we add that damping portion, we get a B theta, theta M, just one dot this time. And we also need to consider what is happening in this lower section. It applies a force or a torque, really a force here, which applies a torque to that rod as well, so we have to take into account everything that's happening. So from there, we will see something really similar. Instead, we'll have JL, theta L, double dot. But this time, because it's going through our two gears, we need to apply our gear ratio N. And the same for the damping of this portion. So we get theta L dot times N. Next thing to do is we're going to take the Laplace transform. So we get tau m in the s domain is equal to j m s squared theta m plus b m s theta m plus j l s squared n theta l plus b l s n theta l. Finally, we want to make sure that we're only looking at our output variable theta L, so we're going to need to convert our theta M to theta L. In order to do that, we want to use our gear ratio. For our angles, it is just going to be reversed. So we have N equal to theta L over theta M, which means that theta M is equal to theta L over N. And we'll just want to plug that in, and then we'll factor out theta L N. So we get tau S equal to theta L N, J M S squared plus B M S, right? Because our theta M's turned into theta L over N, but in order to factor out an N, we have to put this all over N. And we still have that multiplied by 1 over N, so it's going to be squared. Then we add JL S squared plus BL S. The next step is we need to put together all the three equations that we have for our three different systems. In order to do this, we're going to define gains between each system. And the gains kind of define the efficiency of the power transfer from one to the next. We'll start with one called Kg, which is going to relate our voltage through here to our current passing through our very first loop. So for that, we'll get Vg equal to IF times Kg. And our second one is going to be between our current passing through our second loop and the motor of our mechanical system. And we can relate that as the output torque of the motor, tau m, is going to be equal to that current, which is Ig, times our constant, which we'll call Km. Let's use Vg to relate If into Ig, so that we just have one equation for the entire electrical portion of our system. We get Vg equal to Vf Kg over Rf plus Lfs. Okay, and the next step is we want to plug this into our equation here for the current in our second loop. We get Ig equal to Vf Kg Vg over Lg S plus Lfs plus Rg plus Rf times Rf plus Lfs. Now we just have sort of two last steps. We're going to plug this into our relationship between our motor torque and that current, and then we will use this as the new left-hand side of our mechanical system equation. So we get tau m equal to ig, so this whole thing times km, and I'll just rewrite the denominator s plus l f s plus rg r f l f s. And here we have vf, vg. Sorry, there is no vg here. That's what we were plugging in. Sorry, no vg. But there is a kg and a km. Now, the last step is we want to plug this entire equation in as the left-hand side here and just rearrange quickly so that we get our output theta L over our input VF. So I'm just going to do that all in one quick step. So we get theta L over VF. These are both in the S domain, of course. And that is going to be equal to, everything here is going to be in the denominator, and everything we have here will probably stay in the numerator, so we're going to get this multiplied by all of that in the denominator. So here we will have kg, km over top of lgs plus lfs rg rf rf lf, and then multiplied by n and get j s squared plus b s over n squared plus j l s squared plus b l s. That is it. So that is our output transfer function. We have our theta L, which is the angular output for our applied load, and that's divided by our input, which is the voltage across these two nodes. Okay, so the first step is we want to draw kind of a free body diagram so that we can write the equation of motion for the ball relative to the motor torque, and then we'll also write an equation that relates motor torque to that input current. So to start, we have our beam here. Let's say it's rotating about that point, and our ball is right here. It has its x of t position. The question does state to neglect friction, but it doesn't say anything about damping, so we do need to assume that there is some. And we get b x dot. That's just going to oppose the direction of velocity, and it also has gravity. So we get mg, and we want to relate that to here. This angle in here is going to be the same as the angle of our beam, which is phi. So we will get phi. Okay, and when we relate that to here, we just get a component mg sine phi. And we're going to apply the small angle theorem because the question does state that it only moves slightly. So that's going to be approximately equal to mg phi. Okay, and now we can write our equation of motion for that. So we're going to sum forces, and that's going to be equal to mx double dot. So we will get mx double dot equal to, we have our force of gravity pulling us down, which is mg phi, and our damping opposing that. So now that we have that, we need an equation for phi based on the input current. So for that, we'll look at the motor, where we can say that the output torque of the motor is equal to its mass relative to force, but in terms of torque would be its moment of inertia, J, torque equivalent of mass, essentially. So we'll call it Jm, and instead of position, we get our angular acceleration. And that has to be equal to kind of like what we had in the last question, where we get a gain between the input current and the output torque or output angle, which is going to give us I times K. Now we want to take the Laplace transforms of both of these before we put them together. So we get ms squared x equal to mg phi minus bs x. And for the mechanical portion of our system, we will get jms squared phi equal to I k. Rearrange this so that we have an equation for phi equal to I k over jms squared. And finally plug that into our equation of motion, and then we just need to rearrange to get our transfer function. So we'll write that here. We get ms squared x plus bsx, I just moved that to the other side, equal to mg ik over jms squared. I is our input and x is our output, so factor out x, we get ms squared plus bs equal to mg ik over jms squared. And finally rearrange to our transfer function form, where we want our output over our input. So that's always what you want with a transfer function. Our output is x, our input is our current I. Those are both in the S domain. And that is going to be equal to gk over j s. We'll factor out an s here to get s cubed. And don't forget the m in the numerator, sorry. And here we have s plus b over m. If we factor out an m, and then those two will cancel. So what we should get is gk over j s cubed s plus b over m. Or we can rewrite the denominator, because we don't normally want a coefficient in front of our highest order s. So we get x of s over I of s equal to gk over j, all divided by s cubed s plus b over m. And that's it. So just remember, when you're finding your transfer function, it definitely has to be in your frequency domain or the S domain, and it always stands for your output over your input. You can have multiple of them for the same system if you have multiple possible inputs or outputs. Kind of like on some of the earlier questions today, there were multiple outputs. That's it.